the second to last chapter here is going to talk about circles, okay? And then the final chapter will be solids. So those are the last two things that we have left to go through. So if we take a look at circles first. So I'm going to define now. Notice I erased some of my stuff here. I'm going to do a couple definitions down here, starting with what a circle is. Okay, so by definition, a circle, it's a set of points. Now I'm gonna fill this out because I'm leaving it blank for a reason here, but it's a set of points that are a given distance from a fixed point. All right, so notice I have a couple spaces that I left here to fill this in. If you just have the words that are written here, okay, so the set of all points that are a given distance from a fixed point, this is not the actual definition of circle. It's the definition of sphere. And it doesn't limit it to a two-dimensional or a flat surface. And so the word that we need to add here to make sure that this is now the definition of a circle is to add coplanar. And so a circle is a set of all coplanar points that are a given distance. That given distance is called a radius from a fixed point, and that fixed point is called a center. And so adding those words gives a little bit more to demonstrate what we're dealing with. All right, so let's talk a little bit here about the parts of a circle. And so the first is, if we come back up here, the center of a circle. It's that point that's equidistant from all the points on the circle. And so notice the symbol, I'll use that symbol for circle here. So the center of this circle is point P. P is the same distance from C, F, H, N, K, and D, and any other point that you place on the circle itself. And now, coming down here, naming a circle. There's going to be two ways to name a circle. The first way is to name it. The first way to name it is to name it by using its center. And so we could call this circle P. Okay, circle P, you can name a circle by just using its center. The only time that you can't is if you have what's called concentric circles. Concentric circles are coplanar circles that have the same center. Okay, so if you had something like this, where A is the center of these two circles, could you name that circle? Could you identify which of those two circles I'm talking about by calling it circle A? No, right? Because it could represent either of them. And so because you don't know which it is, you cannot name a circle if by its center if it's a concentric circles. Okay? So that's the one sort of exception to that. All right, come back up and we'll finish kind of talking about these definitions. So a radius is going to be a segment whose endpoints are both the center and a point on the circle. Okay, so if you look at this, PC, PF, PH, PN, even though it's not drawn, I could call PK and PD radii as well. Radii is the plural form of radius. Okay, so any segment whose endpoint is the center of the circle and then some point on the circle itself, that's called a radius. Okay, a chord of a circle is defined as a segment whose endpoints are both on the circle. Okay, so here, if you look, D and K, these are two endpoints on the circle, so that would be a chord. Also, point N and C are two endpoints on the circle, so that would be a chord as well. And then the final definition of what you see right here is the diameter. And the diameter is a chord that passes through the center. So here, if you have these two endpoints and it passes through point P, then you're dealing with a diameter. And the diameter is equal to twice the radius when it comes to calculations. Right, the last term that's not on here, but I do want to add, once again, is what's called a central angle. A central angle is an angle whose vertex is the center of a circle. And the sides are going to be radii of the circle. And that's just because it's part of what this question is. We'll talk more about angles and arcs and stuff as well a little bit later, but this is part of a question that you're going to see, so I want to make sure that you have it as a definition. All right, so really quickly, I want you to see if you can answer the questions here. I'm going to erase the markings I put on. Okay, but see if you can answer all of these parts of this question. Oh, let me go back. One more thing. The second method for naming a circle is to pick 3 points on the circle. And so you could have also called this circle, take any combination of D, C, F, H, N, and K. So D, C, F would be an example of that. Any combination of 3 points that lie on that circle, and that will always work to name a circle. All right, so again, go ahead and see if you can answer all parts to this first question, okay, based on those definitions. All right, so working with definitions like you're going to see on this slide and the next slide. If you identify the center, we talked already, the center is point P. A diameter is going to be a segment that passes through the center and has its endpoints on the circle. So NC or CN will work, either order is fine. A radius can be any segment that has P as an endpoint and then the other endpoint is on the circle itself. So PC, PF, PH, PN, you could even have put PK or PD. That would all work. So I'm just going to call it PC for this example, but any of those combinations would work. The order of the naming doesn't matter either. So you could call it CP as well. Next, an accurate way to name a central angle. So a central angle needs to have P as its center, and then the two sides are going to form radii. So the first thing is anything that's not a P as the center, I can eliminate. So I'm going to eliminate those bottom 3 options. And then if I look CPH, that is a central angle. DPH, again, even though it's not drawn here, it represents an angle that can be drawn, so that works. And then finally DPC, same idea. Even though DP isn't a segment that's drawn, it represents that when you name it. And so all 3 of these top options would be acceptable central angles. Okay, and then the final question, which are possible ways to name that circle? Well, first, circle P is using just the center, so that's going to work. And then for the other ones, it's going to be any 3 points that lie on the circle itself. Okay, so I can eliminate these other 2 options with 1 point because those aren't the center. I can eliminate the option with 2 points because you can't name a circle using 2 points. And so now when I look at these remaining ones, I need to make sure that all of the points that are in the name fall on the circle. So H, C, and D, yes, those all fall on the circle. K, D, and N also all fall on the circle. K, D, and P, well, P is the center, so that's not going to work. H, P, and N, P is the center, that's not going to work. So again, the options that do work here are the top 2 plus this circle P would be your naming conventions. All right. The next slide has the sort of the remaining terminology from the anatomy that I want you to be aware of. So all of these, I'm not going to redo those. I'm just going to kind of cross them out, but it's all still the same definition that you saw on the first slide. And I'm going to add these last three. So the next two happen to be names of different types of lines that interact with a circle. A secant is a line that intersects a circle at 2 points. Okay, so here, KH, you have these 2 points, or sorry, that line from K to H passes through the circle at points B and H. Those are the two intersections, and so that would be considered a secant. AD, if we took this diameter right here and you extended it into a line or called it line AD rather than segment AD, then it becomes a secant as well. So secant, just as the name refers to a line, you can also use secant as an adjective to describe a segment or line or ray. Okay, so you can have a line that's secant to a circle, or a secant segment is going to be a portion of that, but that's what the word secant represents. Tangent is going to be a line that intersects at exactly 1 point, or intersects a circle. Exactly 1 point. So here, when you look at this line right here, there's only one intersection, point F, and then it's a line that extends infinitely in each direction. That would be an example of a tangent. The tangent by itself, as a noun, is a line. If you're talking about a portion of that tangent, then you might call it a tangent segment, where you use it as an adjective. Okay. Now, if you had something like this, and we'll call this point X. If you had this line here that intersects the circle at just this 1 point, even though it might visualize it as intersecting at 1 point, the fact that a line extends infinitely means that you would have to extend that down and find the other place where it intersects. So that would actually be a secant, even if it was just modeled with this portion. Okay? But you have to use the definition for a line that extends infinitely through. And then the final definition here is the point of tangency, and that is the actual intersection. Of a tangent to a circle. And so once again, we see that would be point F in this case. All right, so once again, see how far you can get in about a minute or a minute and a half, what I give you, to identify all the parts of the circle that's labeled up above based on this matching question. Okay, so first I need to name a secant. So again, by just the word itself as a noun, it's a line. So I'm going to refer to these two options for lines. Secant is a line that intersects a circle at 2 places. So B and H are 2 points. If I look at that line, that is in fact a secant. So option B is going to be my correct answer there. Okay, name a chord. A chord that is not a diameter. So again, a chord is going to be a segment. So once again, I'm going to look for segments. So there's all my segments. A chord is going to have endpoints on the circle. So if I look at C, J, neither of those are on the circle. JB, J is not on the circle. HB, H and B are on the circle, so that means F would be my option. If I wanted to verify, A and D, those are a chord, but it's also a diameter, so I'm going to call that K for the next one. Oops. And again, I used HB here. And if I wanted to confirm D and C, C is not on the circle, so that one wouldn't fit as well. Next, tangent. A tangent also is a line, so let's come down to option J and test. Is GF a tangent? Yes, it is. It passes right through that point of tangency F, so J would be the option here. And I just said point of tangency F, that's the second to last question, so option A is my point of tangency. Next, naming a radius. A radius will also need to be one of those segments, a segment that includes point C. So when I'm looking C and J, but J is not on the circle, JB, neither, it doesn't contain the C. Here, CD, D is on the circle, so that would be my answer, option L. And then finally, naming the circle. You can name the circle. There's two different ways, either by a single point, which isn't even an option, or A, B, and C. A, B are on the circle, but not C. F, B, D, all three of those points are on the circle, and so that leaves option I for that last problem. And so that would be the matching for those, the anatomy of a circle. All right. So I know it took a longer time to go through just the definitions here than kind of usual, but my expectation is that you will know what I'm referring to if I call a secant or tangent throughout the rest of this chapter, okay? Or chords or diameters, radius, and so on. All right, so let's start with some properties involving tangents. Okay, the first is that when you have a tangent line, a tangent to a circle intersects the radius of the circle at a 90-degree angle. Okay, so that's the relationship that exists here. Another way to put it is that a line is tangent to a circle if and only if the line is perpendicular to the radius. Okay, and so here what you see is that M is going to be tangent. Then you know that QP is perpendicular to line M. Okay. So you're going to be asked two different kind of sets of questions regarding this. The first is going to be one that just asks, is this a tangent line? Okay, so what you can do on something like this is use that same sort of converse of a Pythagorean theorem that we talked about, which was, or if you're testing to see if triangles are acute, obtuse, or right, what we're going to just see is, does the Pythagorean theorem apply? So if we take this first example and we test the sum of the squares of the two legs versus the square of the longest side, are these equal? If they are equal, then the segment ST would be tangent. If it's not, then it would not be tangent. Same with this second scenario. Take 16 squared plus 30 squared, the sum of the squares of the two shorter sides, and compare it to the square of that longer side, and just test to see. Is this relationship true for a right, or does this relationship equal each other where this is a right triangle? So if I take these calculations here, and I compare the sum of the squares versus 34 squared, I get 881 is not equal to 1156. Okay, so I know this is an obtuse angle, or an obtuse triangle. Okay, it's not a right triangle, which means this could not be a tangent segment. Right, if I compare the next, I have 34 squared, so I'm just going to replace these here. I have 16 squared versus 30 squared, and I see that it is 1156 and 1156. Those are equal. The fact that they're equal means, yes, these are in fact a right angle, which means that that would be perpendicular. All right. I want you to try this last question here on this slide. Would be the other way that you would sort of apply this, and that is, if you're being told that it's a tangent, and can you find what missing pieces are, knowing that it's going to form a right triangle, which you can then use Pythagorean theorem to find unknowns. Okay, so see if you can find what would be the value of R in this problem, given that that is a point of tangency. Remember, as you're working through these, you can enter your answers as calculations, okay, but you still may need to know how certain properties work for different types of calculations. So on a problem like this, in order for you to solve for R, what you're going to need to use is the fact that a squared plus b squared has to equal c squared. Okay? Since this is a tangent and a right angle, you can calculate the Pythagorean theorem, where if you take your leg r squared plus your other leg 15 squared, set it equal to your hypotenuse. Notice this whole measure is r plus 12 squared. Okay, so this is your calculation. And so if you just start working through this. Now, I'm not going to calculate it out until the end because I can show you how you can just enter a calculation as your solution this way. But you do need to know, how do you expand a binomial square? R plus 12 quantity squared isn't just r squared plus 12 squared. Okay, you have to account for the property where it's the first term squared, plus it's double the product of your terms. So r times 12 is 12r, double that is 24r. That's your middle term. That's the most common mistake that's made by students, to miss that middle term. And then plus your last term squared. I'm just going to leave it as 12 squared, although it's a common square. You could simplify it if you want. The reason I'm leaving it here is, as you work to solve this, I'm going to subtract r squared from both sides. Those get canceled out. I'm then going to isolate my r by subtracting 12 squared from both sides. So I get 15 squared minus 12 squared is equal to 24r. And then I can divide by 24. So notice to solve for r. So I have my r value written as a calculation, and that's fine. Okay, if I type that in, 15 squared minus 12 squared, and then that whole thing, divide by 24, I get my answer to be 3.375. So that would be an acceptable answer. And remember, you can always enter your answers as a fraction by clicking this show the fraction form. So 27 over 8 would be sort of the other form that you might see the answer in. And any of those are going to work just fine. All right. The second relationship here, before we get to the last two, which are the more challenging ones, is this concept that if you have a tangent segment that originates from the same external point, those segments are going to be exactly the same. And so here's what that means. Or actually, let me write the wording here first. Tangent segments that originate from the same external point are going to be the same length. So here, if I have points of tangency r and t, when I connect those to some common external point out here, s, these are going to be the same. Okay, so what I would have is rs and st are equal to each other in this example. Okay, so based on that relationship, okay, see if you can answer this question below. The lower question is probably a little more straightforward. Okay, but see if you can find what would be the total perimeter of that quadrilateral, okay, if you apply the property that tangent segments that originate from the same exterior point are congruent. All right, if we label what we have here, you're told that AD is 47, AP is 20, PB is 36, and QC is 24. Okay, based on the property that we were just talking about, okay, what we know is that any of these tangent segments that originate from the same point are the same. So AS and AP are the same. PB and BQ are the same. CQ and CR are the same. DR and DS are the same. So once we label these, we can find if AP is 20, then this measure is also 20. If PB is 36, this measure is also 36. If QC is 24, this measure is also 24. And now if we know this whole measure is 47 minus 20 of it being AS, we're left with 27 for DS, which again gives you the measure RD. And once you have all of these, the perimeter is just the sum of all these. Notice that they all come in pairs. So if I just double one from each pair, so if I take 20 plus 36 plus 24 plus 27, and I double that, I would get my answer. So this is my calculation, or calculated value. If I do the actual calculation and find what would that measure be. Oops. I get my answer to be 214. And so, again, either of those forms would be an acceptable way to enter your answer. All right, questions on that relationship? Tangent segments from the same external point are equal or congruent. Okay, so try the top question, see if you can answer that using the same concept. Okay, but now, again, it's working with expressions and solving a multi-step problem. So if we're looking at this, we label what we have. We're told that these tangent segments AB and D and AD, so we know that these two tangent segments that both originate from the same point A are equal to each other. We can label them. DA is 8 times x plus 11. BA is 154 minus 3x. And so what we know is that those have to be equal, right? So AB and AD are the same since they originate from the same exterior point in our tangent. And so that means the expression 154 minus 3x and 8 times x plus 11 are the same. Now, normally I probably wouldn't have written this step down. If I'm working through this, I would probably directly enter the distributed form, the expanded form of this, 8x plus 88. But regardless, you would get to this point right here. If we move all of our x terms to one side and our constants over to the other side, you get 11x is equal to, and here you can leave it as the calculation 154 minus 88, or you can actually do the calculation. Get 66, divide by 11. So we see here that x is equal to 6. This isn't what the question was asking us. The question was asking us to find AB and AD. Now, you could either plug one of those in. So BA is 154 minus 3 times 6. I could do the calculation of that, 154 times 3 times 6, and that would give me my answer of 136. So I could then enter 136 in both of these. I know that these are equal to each other, therefore they're both going to be the same measure. But if I wanted to, I could confirm my answer by plugging in the same value x as 6 into the other calculation if I wanted to. And that would, again, confirm for me that 8 times the quantity 6 plus 11. Does that equal 136? Yes, it does. And so that gives you that extra step of I've confirmed my answer using a different calculation. Therefore, I have a higher level of certainty that I got it right. All right. So those are what I would consider the more straightforward questions that you're going to see in this section. And the next two slides, these last two slides, are going to go through the questions that are a little bit more on the challenging side. And they both involve definitions of terms that we haven't talked about. So the first one is what's called a common internal tangent. And the common internal tangent for this is this tangent segment between two circles. And notice that that tangent segment there passes through this imaginary line connecting the circles, the dashed line. Okay, so this is, by definition, what's called a common internal tangent. Okay, it's a line or a segment that's tangent to two circles. And that intersects that imaginary line between their circle, or between their center. All right, so I'm going to call this y. So this common internal tangent I'm going to refer to as y in this example here. And because in order to solve this, you are going to need to know a couple different things. One, the distance of these centers, so I'll call that d. And then two, the radii of each of these circles. So I'll call R1 and R2 the radius of each circle, R1 being the smaller one, R2 being the larger one. All right, so when you are solving this question, the way that I present it, or the way that I'm going to show you how to solve this, is to square off, or to create a rectangle, basically stack a rectangle onto that common internal tangent. Okay, so if I stack a rectangle right here, I'm going to build this rectangle off of that lower, or off of that smaller triangle. And what I wind up creating right here is I create this large right triangle here, where I have this whole length is the opposite side of the rectangle, which is equal, right? So that's the length of y, my common internal tangent. And then I have my distance d right here is the hypotenuse. And then I have this distance right here. Well, I have my opposite side, r1. So this whole distance is r2 plus r1. And so what I'm able to do is I'm able to create this large right triangle here, which I can then use Pythagorean theorem to solve. And I want you to see if you can apply that concept to this example problem on your own before I actually talk through it. So see if you can kind of follow it just using these instructions. And then I'm going to go through it with you. So if I am applying these properties here to find this measure, what I'm going to do is I see that I have this y value, this common internal tangent. I'm going to build a rectangle onto that or across from that common internal tangent. So this is 90 degrees here, meaning that length is 8, this side is y. And what I wind up having is I have this whole right triangle here. I'm just going to redraw it. I have a length of y, a length of 16 plus this 8, and then I have this distance 30. So here's enough to find my value here. I have y squared plus 24 squared equals 30 squared. Subtract 24 squared from both sides and extract my root. I can either enter my answer as that calculation, or if I do the calculation itself, I get my answer to be 18, and that is the length of y. And notice this y is the same as this y. That's the length of that common internal tangent. Okay. So that's calculating the common internal tangent. The common external tangent is a similar type of process. You're going to build it off of the radii of the two circles. But this time, instead of building a rectangle onto it, you're going to remove a rectangle off of it. Okay, and so here's the common external tangent. Notice it's the same two circles, but now it's the common tangent that does not pass through that imaginary line connecting the centers. Okay, so a common external tangent is the line or segment that's tangent to two circles. But this time it does not pass through the imaginary line joining the centers. And once again, you're going to have all those same pieces. So we'll call this one x here. We have our distance is still designated here d, and we're going to use radius 1 and radius 2 Now remember, these are both at 90 degrees to the point of tangency. So that's where that 90 degrees goes. And what you're going to do to solve for this is going to be to remove a rectangle from that. So notice in this rectangle, opposite side is x, opposite side is r1. It's the same type of triangle, right? We're looking at the common tangent and the radius of the other circle. But notice what's being built here. Okay, so actually, let me talk. This one is going to be to remove a rectangle off of the common internal or common external tangent to form this right triangle. And notice that this angle right here is going to be your right angle. You have your D value. So here's the triangle that we're forming here. The D value stays the same. The X value is opposite the X here. And what you're left with in this portion right here is the whole measure of R2 minus this upper portion here, which was R1. So that last little remaining leg right there is going to be the difference of the radii as the leg of that right triangle. Okay? And then you can use Pythagorean theorem and solve for whatever piece they're asking you to solve for. So once again, just take a moment really quickly. Again, we don't have a ton of time, but see how far you can get on that calculation on your own before I talk through it. And so if I'm looking to remove this rectangle here, I use the properties of a rectangle. Opposite sides are equal. So I have x here, and I have this portion 7. And what I'm going to be looking at or working with is this little right triangle in here, that sliver of a right triangle. This is a 90-degree angle. This hypotenuse is 43. This leg here is x. And what I'm left with is this whole portion is 17 minus this upper portion of 7. So 17 minus 7 is going to give me that remaining side length of 10. And so then I have x squared plus 10 squared equals 43 squared. Subtract 10 squared from both sides and extract my root. And once again, that will give you your calculation. So if I took the square root of 43 squared minus 10 squared, it would give me my answer of 41.82 approximately. Or I could use the calculation itself to give me that answer.